1 second. Can you guys see my screen?
Yes, but not your slides yet. Oh, there you
Yes. There we go. Hello everyone. My name is Shengyi Huang, and I am a third year. Feel free to call me Costa. I'm a third year computer science PhD student working with Dr. Santiago Antonian at Drexel University, and my research focuses on applying deep reinforcement learning to real-time strategy games. In this talk, I'll be presenting our latest work, Action Guidance, Getting the Best of Sparse Rewards and Shape Rewards for Real-Time Strategy Games. So the domain of our paper is in real-time strategy games. That is, how do we create better game artificial intelligence for RTS games? There's a lot of challenges in creating better AIs for RTS games. The first challenge is the real-time decision-making aspect of the game. That is, the agent will only have milliseconds to make a decision, and in comparison to other games such as Go or chess, the agents will usually have up to a minute or two to make a decision. Second, RTS games are partially observable, which means the AI will have limited information to make decisions from. Third, RTS games have extremely large branching factor for search-based approaches. This makes it difficult to directly apply methods such as Monte Carlo tree search. Fourth, RTS games have very sparse rewards for reinforcement learning agents, which is the problem that we're going to try to address in this paper. And the approach that we're using to tackle the challenges in RTS games is reinforcement learning. It is a simple framework where an agent learns in an interactive environment by trial and error, using feedback from its own actions and experiences. To see a demo, refer to the figure on the right. Here, we have the agent symbolized by a brain. The agent makes some actions to the environment, and the environment symbolized by this earth returns some reward and observation back to the agent. And we continue this loop. The agent continues makes actions and receive rewards. The agent will continue until it learns what are the best actions that could receive in high rewards. Reinforcement learning has achieved great success in games such as Dota 2 and StarCraft 2. And the core problem that we're trying to address is how do we manage sparse rewards in RTS games? So if we want to train the agent using reinforcement learning, we have to supply rewards to train the agent. And the natural reward in RTS games is very sparse, which is +1 for winning, -1 for losing, and 0 for drawing. So if we use this, the plus side of the sparse reward is that this is the real objective. And if we manage to train the reinforcement learning to learn this sparse reward, then the reinforcement learning agent can learn to win a game, as many as it can. The downside is that this is, in practice, usually too difficult for the agent to learn anything, because usually when we initialize a reinforcement learning agent, it performs actions by chance, and it is very unlikely that it will receive the first sparse reward of winning by just pure chance. To address this problem, a common approach is to use shaped rewards. So that is to create intermediate rewards to encourage good things from happening. So for example, we'll give some rewards for winning, give some rewards for harvesting resources, returning resources, producing workers, and so on. The plus side is that this is easier to learn, but the downside is that the agent might optimize for the shape rewards instead of the real objective. So to see this in action, here on the left is the agent trained with the shaped reward. And what I found interesting is that agent will continue attack the enemy base until the enemy base only has 1 HP left, and then the agent will go back to the base again and start producing workers and combat units. This obviously optimizes the shape rewards because it's doing a lot of good things like producing workers. However, it's not optimizing against the real objective of winning the game as fast as possible. Here on the right, we have the agent trained with a sparse reward. And because this is way too difficult, even after 10 million frames of training, the agent still doesn't learn any useful policy. And here, when we see the episodic return in the shape rewards, we find that the agent trained with a shape reward is able to consistently learn good behaviors in a steady pace during the course of its training. But when we evaluate the agent's performance in the sparse reward setting, that is, we evaluate the agent's performance in how many games it can win, we find that the agent trained with the shape rewards actually performs only a little better than the agent trained with a sparse reward. That is, they draw most of the time, center around a 0 reward. So if the agent would win, it'll achieve 1. In this paper, we present a novel technique that we call action guidance that is almost as sample efficient as shape rewards, but eventually optimizes the true objective of sparse rewards. Here is an intuitive demo of how it works. Instead of only creating one reinforcement learning, we create multiple reinforcement learning agents. We create the first agent, which we call the main agent, that only learns from the sparse reward function. And then we create auxiliary agents that learn from shape reward functions. And we set a probability P of taking action guidance from auxiliary agents. That is, the main agent will execute the off-policy action sampled from these auxiliary agents. The intuition is that in the initial stages of the training, we set a really high P. Then the auxiliary agent will make the training efficient because the auxiliary agents, they learn from the shape reward function that are easier to learn. As we decrease this P to 0, the main agent gets more independent and starts to optimize against the real objective. Action guidance, therefore, gets the best of both worlds of shape and sparse rewards. Another way to look at it is the main agent basically imitate actions from the auxiliary agent. And by imitating, the main agent gets closer to the sparse reward. And once it gets the sparse reward, the main agent can optimize for it. And this is, again, how it kind of works, a demo. Here on the left, you have the agent trained with a shape reward that learns a lot of good behaviors, but does not learn to win the game as fast as possible. On the right, you have the agent trained with action guidance. So the video finishes within 1 or 2 seconds because the agent does a worker rush and just finish the game within 1 second or 2. So which is one efficient way to win the game as fast as possible. When we see this in episodic return in the sparse rewards, we found that as we decrease the probability of sampling actions from the auxiliary agent, as we decrease this probability from 95% to 0, the main agent of action guidance starts to optimize against the real objective. In comparison, when training agent with sparse reward and shape rewards, the agents draws the game most of the time. So to delve into a little details of action guidance, I'll be go over some of the details in a high level. If you want to know the specifics of the theory and notations, please refer to our paper. But we basically have some notations about MDP, and we have a stochastic policy which we denote pi theta that is parameterized by some parameter theta. And the basic idea is we create different MDPs for the main agents and the auxiliary agents. They share the same states, observation and action space, but they have different reward functions. And for each of these MDP, we create a policy for them, and we use pi s to denote the set of these policies. And this is how action guidance learn. At each time step t, during the rollouts, we use some exploration strategy to select a policy pi b from pi s. A pi b is also known as a behavior policy to sample an action. And when the episode ends, each policy in pi s, including the policy for the main agent and the auxiliary agents, can be updated via its off-policy policy gradient, which is this term right here. However, this term is known to cause high variance, so in practice, we clip it the same way as the proximal policy optimization, PPO. To make action guidance into a practical algorithm, there are other things to consider. So action guidance can leverage multiple auxiliary agents, but in practice, we only use one auxiliary agent for the simplicity of the experiments. Additionally, we use epsilon greedy as exploration strategy. So we create this shift period in which we'll have a 95% probability of sampling actions from the auxiliary agent, and we have this adaptation period where we have the main agent gradually adapt and become independent. So we decrease this 95% probability gradually to 0. We also have a optimization that we call positive learning optimization, that basically the intuition is to learn from good experiences. So we skip the gradient update if the reward is 0. Without this positive learning optimization, what we found is that the main agent of the action guidance will be flooded with a lot of trajectories with 0 rewards. And as a result, here on the right, you see the entropy of the main agent, it prematurely converges. In comparison, if we use a positive learning optimization, then its entropy stays a little higher. And as a result, for all of our experiments in produced combat units, the agent is able to converge versus without PLO, a lot of them just kind of not learning anything in the end. For the evaluation environment, we use micro-RTS as our test bed, and we also use Gym micro-RTS as the reinforcement learning environments. And there are 3 tasks that we examined. All three of them are sparse rewards tasks. The first is learning to attack. This is difficult because the agent will have to move from one end of the map to the other end of the map to attack the enemy. But the action space is so large, so for most of the time, the agent just kind of stays within its own region and not really exploring the other side of the map. The second task is produce combat units. So the agent will have to learn to produce barracks and produce harvesting resources, and then starts to produce combat units. And it has to keep harvesting resources. And it also has to move the combat units out of the way so new combat units can be produced. So there's a lot of actions involved, even though it seems to be a simple task. And then the third task is the most difficult, where we only give the match outcome reward as a reward. So -1 on loss, 0 on draw, and +1 on win. For each of these 3 tasks, we also manually design a shape reward function. So here are the agents that we compare. We have an agent that only trained with the sparse reward, and then we have an agent that trained with the shape reward. And then for our action guidance related experiments, we consider 3 hyperparameters. The first one has a longer adaptation period, and then the second one has a shorter adaptation period. And the third one is a mixed policy, where instead of decreasing the probability of sampling actions from the auxiliary agent to 0, we decrease it to 50%. In that case, we sort of have this 2 policies. The main agent and the auxiliary agent, both of them have 50% of a chance to issue an action. And here are our evaluation results. First, action guidance is sample efficient. Here you see the episodic return according to the sparse reward in produced combat units. We see that the action guidance related experiments, which are the blue and the brown lines, we see them move up at the same pace as the red line, which is the agent trained with the shape reward, which means action guidance is sample efficient. In comparison, the agent trained with sparse reward, for the most part, during the entire course of this training, never gets the first sparse reward. The second result is action guidance optimizes the real objective. So again, using the example in produced combat units, we see that as we decrease the probability of sampling actions from the auxiliary agent, we find that the majority of the shape reward of the action guidance agent starts to decrease, and then the main agent starts to optimize against the real objective. So that's why you see this performance dip. And then when we see the behaviors they learn in action, so this is the agent trained with shape rewards, and we found that it only produces combat units once all of the resources are exhausted. In comparison, the agent trained with action guidance is able to produce combat units and harvest resources concurrently. This is a much more desirable behavior because should the enemy comes early, the agent will have enough combat units to defend. And it is because of this performance drop that the main agent of the action guidance agent starts to optimize against the real objective of producing combat units instead of optimizing against the shape reward of harvesting resources and producing combat units. Additionally, we found that the hyperparameters adaptation and shift matter. So in more difficult tasks such as defeat random enemy, we find having a longer adaptation generally helps with the main agent. Setting a short adaptation, the agent doesn't learn anything. In comparison, in less difficult tasks such as produce combat units, we find the agent trained with shorter adaptation is able to perform better. But also, more importantly, it learns this kind of behavior. And had we trained the agent using a longer adaptation with action guidance, the agent will learn behavior that is no different from the shape reward. The intuitive explanation is that having a higher adaptation gives more guidance to the agent, so the agent learns harder tasks, but it also inflicts more bias on how the task should be performed. Setting a lower adaptation means that the agent will have less bias and possibly have a better chance to optimize for a categorically better behavior. Additionally, we find the PLO results are inconclusive. In some tasks, PLO helps really much. So, for example, in defeat random enemy, we find that PLO really helps with long adaptation. But in produced combat units, we find that PLO actually hurts the performance for the long adaptation agent. But in produced combat units with the short adaptation, PLO helps a lot too. But more importantly, if we implement PLO with the agent trained with the sparse reward, we find that the agent is not able to learn anything with PLO. So this suggests that PLO is code-level optimization that is very specific to action guidance. Lastly, action guidance mixed policy is viable. So in a sense, they are our best agents. They perform very competitively in all three tasks we evaluated. This suggests that we can almost consider the main agent and the auxiliary agent as a joint entity making joint decisions together, and somehow they're able to perform very well in all of the tasks that we examined. In conclusion, in this paper, we present a novel technique that we call action guidance that is almost as sample efficient as shape rewards, but eventually optimizes the true objective of sparse rewards. Compared to previous work, in AlphaStar, AlphaStar uses imitation learning to bootstrap an agent, so it requires human replay, but it eventually optimizes the sparse reward. In OpenAI 5, they use shape rewards, which makes the training sample efficient and does not require human replay, but they don't eventually optimize the sparse rewards. In action guidance, we are sample efficient, we do not require human replay, and we eventually optimize the sparse rewards. So action guidance hopefully will serve as a good, sort of a promising intermediate between these two approaches. That is for my presentation. I encourage you to check out our interactive report, which contains our experiments and everything. You can check out source code, hyperparameters, and videos of the agents playing the game. And here are our source code, and because of the conference proceedings now out, here's a link to the preprint of our paper. Thank you.
Thanks, Costa.
Thank you.
All right, so we have a few minutes for questions. So.
I have one.
Yes.
So I'm not the biggest expert on reward shaping, but as far as I understand, if you do reward shaping properly and you do it in a potential-based way, then you don't actually change the optimal policy. Have you tried that? I mean, wouldn't that solve the problem to some degree?
So potential-based, the reward shaping is difficult to design because it is a state-based reward shaping. So you need to essentially say if you reach a better state, you have better rewards. But in real-time strategy games, there are a lot of states that we don't know what are the best reward function. We don't know if one state is necessarily better than the other. So for potential-based, I think it takes a lot of effort to engineer. Obviously, it can work very well if you spend a lot of effort to tune it. But action guidance is sort of like another alternative to do this. And in a way, you can just design reward shaping, I guess, in a more lenient way. And then because the agent optimizes sparse reward, it will still learn the desirable behavior.
Excellent. Any other questions?
Thank you.
All right. So if there's no more questions, so one quick comment. So Costa used this. You mentioned it very quickly, but there's a micro RTS gym environment. So Costa prepared a gym environment, like an OpenAI gym environment for micro RTS that in the afternoon he will show in case anyone is interested in doing reinforcement learning with this environment.
Sounds good.
All right. So we go into our first break. So we have a 15-minute break, and we will reconvene at 12:15 if you're in the East Coast, 9:15 if you're in the West Coast. Oops, so want to say something? All right. So we're in a break.
Thanks, Santi. How do I stop this?